right, thanks very much, Dr. Basone, for the opportunity to present the second part of this presentation. So last week we looked at some errors in research with the most pertinent, like on a broadly speaking, you have two types, that is random error and systematic error. And we saw that among the two of these, increasing the sample size doesn't really control for systematic error. So it's always important to think about this when you are planning the study, implementing and doing data analysis. And also like the three main types of systematic errors include selection bias, information bias, and confounding. And a bit more like, let me maybe highlight some of the things we saw last week on confounding. This occurs when you have a third variable, which kind of distorts the relationship between an exposure and an outcome. And this third variable could be so strong in such a way that it could lead to something like, or give like a false impression of there is an association between an exposure and an outcome, which in reality there is none. And in that case, we say that is a spurious association between the exposure and the outcome. And normally, for every research, when you have highlighted your research question using the PICO, if you are doing an interventional study, or a PECO, if you're doing an observational study, you always want to clearly label all of the potential third variables. Your third variable could be a compounder, an effect modifier, a mediator, and a collider. And depending on the label these different third variables take, the way you adjust for them or the way you account for them during the analysis phase also matters. And as we saw last week, the three fundamental conditions for a third variable to be a compounder is that it is associated with the exposure and it causes the outcome. So you have these two associations here, and it is not in the causal pathway, or it doesn't come as a result of the exposure. So here I'll start from first principles, and then from here we'll build up. So this is just a fictitious example where I have my variable A, which causes X and causes Y. But with example, which we have this variable A, and we see that A is related to X and is related to Y, but has no relationship whatsoever to do with X. So I create this now and I do some exploration. Of course, there's a perfect linear relationship between these two variables and A, for example. And here I'm exploring the relationship between these variables. So we have a perfect linear or a clear linear relationship between X and A, and we have a clear linear relationship between Y and A. But now, and also when I go further and I do a correlation matrix between all of these, we see that between A and the different variables, that is X and Y, we have a strong positive correlation between them. But now when I go further to evaluate the effect of Y on X, note that for Y and X there was no relationship or whatsoever to do with them when we created these variables from conception. So when I regress on X, when I use A as my predictor, we see that of course this is significant. And now when I do a regression model with Y on X, this had no relationship, but because this was completely confounded by A and I'm not controlling for A in my model, what happens is that I see this relationship between now X and my Y, which is indicating that a unit increase in X leads to a unit increase or leads to this change in the mean of Y. But now when I control for the variable, so when I control this third variable, which is A, which had no relationship to with which has a direct relationship between X and Y. When I do this now, you see that my third variable becomes significant, but now this one, which is the relationship between Y and X, now is no more significant because from conception, these two variables had no relationship. So this is a good example of confounding. Now I'll move to something which is in real life. So I'll talk a bit about this. I'll use two cases. The first one will be looking at heart rate and mortality. So 1 year mortality in heart failure patients were recruited in the Douala heart failure registry in Cameroon. So I used the PACO criteria here because we are doing with an observational study, specifically a cohort study. So what was my population? The population of the P here was the heart failure patients enrolled in Douala heart failure registry. And the exposure was high heart rate. Well, in this case, I'm hypothesizing that a higher heart rate, people with higher heart rate have higher risk of mortality. And also normal heart rate is considered as my control group. And the outcome here is the 1 year mortality. So here I have this my directed acyclic graph, which kind of links, like we know that uh, fundamentally a higher heart rate is associated with higher mortality. This has been established in literature. So that is how you kind of lay emphasis on which variable is related with which. And theoretically, is age related with heart rate? Yeah, because you have older participants due to some degeneration, they could have a lower heart rate. And is age related to 1 year mortality? Of course, you expect that older participants will have a higher risk of mortality. So when I do this now to explore this further, before I even go further into any regression analysis, the first thing I do is I check for anything which is related to a selection bias. Selection bias in the context of a cohort study here will be related to loss to follow-up. So here I wanted to see if there was any relationship between the sensor, that is participants who were kind of lost to follow-up before the end of the study, and the different variables I've selected. So this is the age categories of the participants, and I splitted the heart rate into different quintiles. And here, good enough, we don't see any clear relationship between the different exposures or the potential variables and the status of loss to follow-up, highlighting that maybe loss to follow-up is not really a strong indication of selection bias in this study. So normally, for data which has to do with time to event, we have to incorporate the time of follow-up in the analysis, and we can do this using Kaplan-Meier curves and or to test for the effect between the different groups. We can do either a log rank test if we have just one categorical variable, or we can go further to do a Cox regression. So as we can clearly see here, when I plot these Kaplan-Meier curves for heart rate, we see that participants with the higher heart rate, you see that the survival probability is lower compared to those who have a normal heart rate. And when I do a log rank test, that is when I compare the mortality across these different categories, taking into account the effect of time, which makes now the log rank test, we see that this is significant. And when I compare the different categories for age, this is not significant, but this is very important because, as I mentioned last week, confounding is something which is a population phenomenon. Is not only something which is found in your data. So even if in this scenario we see that age is not related to my outcome here, which is the 1 year mortality. If I want to go further in my model, it doesn't mean that I drop this and I don't control for it. I don't control for it when I'm doing further analysis or when I'm looking at the Cox regression. So now I have I get the unadjusted. So here now I get the unadjusted heart rate or hazard ratio for the 1 year mortality related to my two selected variables, which is the age categories and the heart rate quintiles. Here we see that compared to participants who have this heart rate of less than 66 beats per minute, as the heart rate increases, we see that also the risk of mortality increases, and we can see that there is a trend. But here we see that there is no relationship between age category and the outcome, or the age of the participants and the outcome. And although this is not significant normally, because this has been established in literature as a potential confounder, even if I don't find it as even if I don't find a statistically significant relationship between these in my model, the best approach to do is that I fit something, a model that adjusts for this effect. That is, I adjust the hazard ratio, or I present an adjusted hazard ratio for heart rate and for the effect of heart rate and 1 year mortality, while accounting for the age of the participants. Of course, if we want to go with the aspect of 10 to 15% change in the effect size to determine if there is a confounding or not, of course, this will not work in this case. But the most important thing is that it is good to understand that confounding is something which comes from the population and not just from your sample, because you could pick maybe a sample that is not very representative and you will not find these associations. But if it has been established in literature, then definitely it's something to control. So the second scenario, or the second case that I want to look at, or that I want to point to, is the 3-year mortality related to chronic kidney disease. So here we have the exposure, which is CKD, and the comparison group here is people without CKD. So here, the first thing I do is that I did some literature search. I tried to see if there's any relationship between these variables, and then I came up with my directed acyclic graph. So we have the age of the participants, which is the potential third variable. In this case, I'm considering it as a confounder. So I normally in literature, or theoretically, chronic kidney disease is associated with mortality. That is 36 months mortality. And age is related to CKD, and age is related uh, to the 36 months of mortality as well. So now we go further to explore the data to see if there's any relationship in terms of selection bias that is related to loss to follow-up. And here we see that for chronic kidney disease, the number of participants who were lost to follow-up, we see that a majority of, or there's a significant relationship between this and the status of being lost to follow-up. So this is something that definitely, even when you get your results, you want to keep in mind, because even if you don't have a confounding, or even if you don't have confounding, or even if you still have confounding in your analysis, you have to take care of the other different types of biases. And as we mentioned last time, information bias and selection bias is something that cannot really be controlled during the analysis. So if I have this kind of significant results, which is kind of indicating that there was a selection bias, like more of people who had chronic disease kind of were at the loss to follow-up, then of course my conclusions I will kind of hinge my conclusions on this, and not be really too optimistic in the way I make the association between these exposures. So I went further to do what is called the log rank test, and to plot the Kaplan-Meier curves. And as you can see here, you see that people with chronic kidney disease have a lower survival probability over the 36 months. And when I compare this using the log rank test, the p-value was less than 0.01. So the next step or what I did was I kind of used this as individual exposures for my Cox regression model. So these are just univariable Cox regression models. And as we can see, participants with chronic kidney disease, they have like a 152% increase in like the hazard ratio is 2.52. And this is significant at the 95% confidence interval. And The next step, still, this is not significant. Of course, this for H is not significant and is similar to what we had in the previous step. But because literature has identified this as a potential confounder, what we have to, or the best approach to do is to adjust this when we are looking or when we are controlling or when we are fitting now the multivariate Cox regression model. Of course, I did not check all of the other things like the assumptions of proportionality because that is not really the point or the importance of the presentation. But normally, before you interpret your model, you want to ensure that all of the assumptions are met. And I think this is it for like the two cases that we had. I did not really